I want you to try something for a second. It might feel a little silly, but
Yeah.
just stare at the empty space right in front of you. Go on, just look at it.
Mm-hmm.
It looks completely empty, doesn't it? It looks still. If you're inside, the air feels dead. If you're outside on a calm day, maybe there's a little drift. But mostly it just seems like nothing is happening.
Right. We treat it like it's a void.
We treat the air like it's just this empty space we move through. But here is where we are dead wrong. That empty space is actually a chaotic, hidden world of violent motion. It is never, ever still.
It's one of the biggest illusions of our daily life, really.
Oh.
Our senses tell us the air is static. But if you could see the physics, I mean, if you could zoom into the atomic level, you'd see a riot.
And that is exactly what we're doing today. We are tearing down that illusion. We're decoding the science of the skies. Our mission is to trace the journey of wind, but not just, the breeze that messes up your hair.
No, we're going bigger.
We are going to find out how microscopic particles, things we can't even see, somehow team up, organize, and eventually grow into the massive city-destroying monsters we call hurricanes and cyclones.
It's a fascinating progression because we usually think of wind as a single object, right?
Yeah, like a wall of air hitting you.
Exactly. But when you really dig into the research we have for today, you realize wind isn't a thing at all. It's a result. It's the outcome of complex planetary mechanics trying to fix an imbalance.
That's the hook for me. We need to figure out the recipe. How do you go from a tiny, invisible particle just vibrating in a room to a storm system that creates a 20-foot wall of water? Because, and this is the crazy part, the source material suggests the ingredients are exactly the same.
They are. It's purely a question of intensity and scale. The physics of a draft in your hallway are surprisingly similar to the physics of a Category 5 storm.
Then let's get into the kitchen and look at these ingredients. We have to start at the micro level. I mentioned that the air is never still. I was reading through the notes on particle physics, and I found this term that sounded more like a sci-fi concept than meteorology. Olorati.
It does sound sci-fi, doesn't it? But olorati essentially refers to a state of readiness. It's a chaotic state. Even when the air feels dead calm to you, the molecules in it are vibrating, spinning, and moving at incredible speeds. They are constantly colliding.
I've heard this described before, but I always assumed it was just random buzzing, like white noise. But the research implies it's more than just noise.
Think of it less like random noise and more like a crowd in a stadium before the game starts.
Okay.
Everyone is moving, shifting, bumping into each other. They aren't going anywhere yet.
Yeah.
But the potential energy is massive. They are in a state of high readiness. They aren't sleeping. They're waiting for a signal.
But here's what I don't get. If I have billions of gas molecules just bouncing off each other like frantic billiard balls, that's just chaos. How does that turn into wind? How do they all agree to move left at the same time?
That is the million-dollar question. It's not magic. It's about dispersion and collision. When a planetary force, which we'll get to, pushes them, they don't just move in a straight line. They collide with their neighbors.
Yeah.
And the source material uses this brilliant analogy of consultants to explain it.
I laughed when I saw that, comparing air particles to consultants in a boardroom.
It's surprisingly accurate, though. Imagine you have a room full of consultants who all have different opinions. They're the particles. They interact. They argue, they collide. Eventually, through all that interaction, they start to influence one another. They build a consensus.
So instead of one particle going north and another going south, they bump into each other enough times that they sort of say, okay, I guess we're all going northeast now.
Precisely. They organize. The chaos of olorati transforms into a collective flow. They start to form a spiral pattern. And that spiral pattern, that collective decision of trillions of consultant particles moving together, that is what you feel on your skin as wind.
It's basically a massive board meeting of air particles that finally decided on a strategy.
In a way, yes. But here's the catch. Consultants rarely decide on a strategy without a CEO telling them what the goals are. These particles aren't deciding on their own. They are being pushed and twisted by much larger forces.
So we have to talk about the stage they're dancing on. The Earth itself.
And specifically the fact that the stage is spinning.
The Coriolis effect. I feel like this is one of those terms everyone hears in high school geography, memorizes for the test, and then immediately forgets how it actually works. I know it spins the wind, but I've never really grasped why. Why does the Earth spinning make the wind curve?
It is counterintuitive. Let's break it down without the complex equations. The Earth spins toward the east, right? But because the Earth is a sphere, It's much wider at the equator than it is near the poles.
Right. The equator is the fat part of the sphere.
Exactly. So if you're standing on the equator, you have to travel a huge distance to make one full rotation in 24 hours. You're physically moving at about 1,000 miles per hour just by standing there.
Okay, I'm with you. I'm moving 1,000 miles per hour east.
Now, imagine you're in New York or London. You're close to the pole. The circle you have to travel in 24 hours is much smaller, so you're moving slower. Maybe only 700 or 800 miles per hour.
So the equator is moving faster than the poles.
Much faster. Now, imagine a parcel of air, our group of consultants, starts at the equator and gets pushed north toward New York. That air still has the momentum of the equator. It's traveling east at 1,000 miles per hour.
But the ground in New York is only moving at 800 miles per hour.
Exactly. The air is moving faster than the ground it's flying over. So from the ground, it looks like it's curving ahead. Towards the east, it's deflecting.
Oh, that makes sense. It's like throwing a ball from a moving car. The ball keeps the speed of the car, even if the person standing on the sidewalk is moving slower.
That is the Coriolis force. It's the difference in speed between the air and the ground below it. This twist is what shapes every single storm system on the planet.
And this is where the hemisphere thing comes in, right? It creates that mirrored effect.
It's a tale of two hemispheres. In the northern hemisphere, this force deflects winds to the right, creating an anti-clockwise spin for storms.
And for our listeners in Sydney or Cape Town?
In the southern hemisphere, the deflection is to the left, creating a clockwise spin.
It's wild that simply crossing the equator flips the entire physics script. If you look at satellite footage, you can literally see this. The hurricane isn't just a blob, it's a beautiful, terrifying spiral. That's the Earth twisting the wind.
It is. So now we have the particles buzzing in chaos, they're organizing into groups, and they're being twisted by the Earth's rotation. But we're missing the most important part.
The engine.
The engine. A car has wheels and a steering wheel, but it needs an engine. Something has to push this air to make it move in the first place.
The power source. And I'm guessing that's the sun.
The sun is the initial spark. It heats the Earth. But the key is that it heats it unevenly. The equator gets scorched, the poles stay icy, land heats up fast, oceans heat up slow.
And nature hates imbalance.
Nature despises it. It wants to equalize the temperature. And this triggers the convection loop. This is the heartbeat of the atmosphere.
Let's walk through this loop because I really want to understand the mechanism. Step one is the heat, right? You have a hot zone.
Right. Solar radiation hits a patch of ground or ocean. The air right above it gets hot. As it heats up, the molecules get excited, back to our consultants, and they spread out. The air becomes less dense.
And like a hot air balloon, it rises.
It shoots upward. That's the updraft. But as it rises into the upper atmosphere, it moves away from the warm Earth. It starts to cool down.
So it hits the ceiling and spreads out.
It cools and spreads. But now look at what's happening down on the ground. You have all this air leaving the surface, shooting up. It leaves a gap, a partial vacuum.
Low pressure.
Exactly. Low pressure just means there is literally less air weighing down on that spot because it's all rising. Now, nature has to fill that gap. So cool, dense air from neighboring areas, places that weren't heated as much, sinks down and rushes in to replace the rising air.
And that rushing air, that is a wind.
That is the wind. Wind is just air rushing from a high-pressure area to fill a low-pressure gap.
This brings us to a term in the notes that sounded technical, but I think we can crack it. The pressure gradient.
It sounds scary, but think of it like a ski slope. Pressure is the altitude. High pressure is the top of the mountain. Low pressure is the bottom. Air is the skier.
It always wants to go down the hill.
Always.
So the gradient is just how steep the slope is.
Perfectly put. If the difference between the high and low pressure is small, a gentle hill, the skier glides slowly, a gentle breeze. But if you have a massive low-pressure vacuum right next to a massive high-pressure wall,
that's a double black diamond slope.
incredible speeds. The steeper the gradient, the faster the wind.
So if you combine all this, you have air rushing down a steep pressure slope, and as it rushes, the Coriolis effect grabs it and twists it into a spiral.
And that is the basic anatomy of a storm.
Okay, so that gets us a storm, maybe a nasty thunderstorm or a gale. But we promise the listeners monsters. We are talking about events that define generations, what pushes the system over the edge, what is the difference between a bad Tuesday and a Category 5 catastrophe.
We need to talk about fuel. High-octane fuel. A standard storm runs on temperature differences. A tropical cyclone runs on the ocean itself.
The source material was very specific about a number here, a critical threshold.
Yes. For a cyclone to form, the sea surface temperature needs to be above 26 or 27 degrees Celsius.
That's warm. That's pleasant swimming water. Why is that specific temperature the magic number?
Because at that temperature, the water doesn't just sit there. It evaporates at a massive rate. It pumps huge amounts of moisture into the air. And this introduces a concept that is often misunderstood. Latent heat.
I remember struggling with this in physics. Latent means hidden, right?
Yes. Think about it. To turn liquid water into gas or vapor, you have to put heat into it. You boil it. That heat energy creates the vapor. But where does that heat go? It's trapped inside the vapor molecule. It's hidden.
It's carrying the energy in a backpack.
Exactly. Now, that warm, wet air rises. It gets high up in the atmosphere and cools down. The vapor turns back into liquid water. It creates clouds and rain. But here's the trick. When it turns back into liquid, it releases that heat from the backpack.
Wait, so when a cloud forms, it releases heat.
Enormous amounts of heat. A thunderstorm isn't just rain, it's a massive heating engine. This released heat warms the air around it even more, which makes the air rise even faster.
Which creates an even stronger vacuum at the bottom.
Yes. Which sucks up even more moisture from the ocean, which rises, condenses, releases more heat, which makes the air rise faster.
It's a feedback loop. It's feeding itself.
It's a runaway thermal engine. The thunderstorm is the battery. The source material emphasizes that thunder and lightning aren't just scary sound effects.
Yep.
They are evidence of this massive energy exchange. As long as that storm sits over warm water, 27 degrees plus, it is eating the ocean's heat and growing stronger every second.
That is terrifying. It's not just wind blowing. It's a heat engine harvesting the ocean. This explains why they die out when they hit land. You cut the fuel line.
Exactly. No warm water, no latent heat. The engine sputters out.
Let's talk about what happens when that engine is running at full capacity. We've gone from consultant particles to a self-feeding monster. The source material contrasts ordinary wind with mega hurricanes.
And the difference in scale is hard to comprehend.
An ordinary wind, maybe a stiff breeze. What are we looking at?
You're looking at pressure gradients that are manageable. Speeds of, say, 30 to 60 kilometers per hour. It knocks over your lawn chair. It's annoying.
But a mega hurricane.
Now you have a pressure vacuum that is off the charts. You have global wind patterns aligning. You have maximum latent heat release. You are looking at speeds exceeding 200, sometimes 300 kilometers per hour.
300 kilometers per hour, that's not a wind, that's a bullet train.
It ceases to behave like a gas. At those speeds, air acts like a solid. If you stick your hand out of a car at 60, you feel resistance. At 300, the air carries enough force to pulverize wood.
The source material highlights 3 specific case studies to show us what this looks like in reality. And I want to spend a moment on these because they aren't just statistics.
No, they're tragedies defined by geography and physics.
The first one is the Bhola cyclone from 1970. I hadn't realized the scale of this one until I read the notes.
Bhola is often cited as the deadliest tropical cyclone in recorded history. It struck East Pakistan, now Bangladesh, and India's West Bengal. The problem there wasn't just the wind speed, it was the geography. The Bay of Bengal is shaped like a funnel.
A funnel?
It narrows as you go north, so the storm pushed a massive wall of water, a storm surge, into this narrowing funnel. The water had nowhere to go but over the land. It wiped out entire islands. The loss of life was staggering, estimated anywhere from 300,000 to 500,000 people.
500,000 people from one storm.
Yeah.
That shows the power of that latent heat engine we talked about.
It does. Then you have a modern example that many listeners will remember. 2005. Hurricane Katrina.
New Orleans.
Katrina taught us a different lesson. It wasn't the strongest storm ever in terms of wind speed when it made landfall, but it hit a vulnerability. New Orleans sits in a bowl below sea level.
And the storm surge.
The low pressure of the hurricane literally sucked the ocean surface upward, and the winds pushed it ashore. The levees failed. It showed that even a modern industrialized superpower isn't immune to these forces. It wasn't just the wind. It was the total system failure caused by the water displacement.
And the third one mentioned, which I think holds the record for sheer wind ferocity in the text, is Haiyan in 2013.
Super Typhoon Haiyan in the Philippines. This was a beast of a different nature. The wind speeds at landfall were estimated at 315 kilometers per hour.
315. I can't even imagine what that sounds like.
Survivors described it not as a wind, but as the sound of a 747 jet taking off inside their living room. At that speed, the air itself becomes a weapon. It stripped bark off trees. It turned debris into missiles. It demonstrated the upper physical limits of what our atmosphere can do.
And to think, all of that power, that 315 kilometer per hour force that stripped the bark off trees, started with those little particles in Olerati, just vibrating.
It really is a domino effect. One collision leads to organization, which catches the spin of the Earth, which feeds on the heat of the sun, which then drinks the heat of the ocean.
So let's synthesize this. We promised a recipe for disaster. If you are a mad scientist and you want to cook up a Hurricane Haiyan, what do you need in the pot?
You need 5 key ingredients. First, you need the chaos. You need the air particles in that Olarati or ready state.
Step 1, the ingredients are prepped.
Step 2, you need spin. You need the Earth's rotation and the Coriolis effect. You need to be far enough from the equator that the spin actually takes effect, usually at least 5 degrees latitude away.
If you're right on the equator, no Coriolis, no hurricane.
Exactly. It's why you almost never see hurricanes cross the equator. They lose their spin.
Okay, step 3.
Solar heat. You need the sun to start the convection loop, creating that initial low pressure.
Step 4.
A steep pressure gradient. You need a deep, deep low pressure center to act as a vacuum cleaner for the surrounding air.
And the final kick.
The fuel. Ocean water. Specifically, water warmer than 26 degrees Celsius, running deep enough to sustain that latent heat battery we talked about.
Chaos, spin, sun, pressure, and warm ocean.
Combine them, and you have the most powerful engine on the planet.
You know, it's actually kind of beautiful in a terrifying way.
It is. And what I find most fascinating, and maybe a bit humbling, is that there are no evil ingredients here. It's just heat and water, sun and earth. These are the exact things that allow life to exist.
Right, we need the sun to live. We need the convection loop to move rain around so we can grow crops.
Exactly. A hurricane isn't nature trying to kill us. It's nature trying to balance itself. It's the atmosphere trying to move excess heat from the equator to the poles. We just happen to be in the way of the furniture being moved.
We are tiny obstacles in a global heat transfer system.
We're living inside a fluid dynamic machine, and we tend to forget that. We build static concrete cities in a world made of swirling gas and water.
Well, we promised a deep dive, and I think we found the bottom. From the microscopic dance of consultant particles to the Olarati chaos, all the way up to the screaming winds of Haiyan. It's all the same air.
It's a powerful perspective shift.
So here is a final thought for you to chew on. The next time you step outside, maybe tomorrow morning, and you feel a gentle breeze on your face, don't just ignore it.
Feel the temperature.
Feel the pressure. Remember that the breeze touching your face is made of the exact same components as the storm that broke the levees in New Orleans. The only difference is the setting on the dial. The recipe is the same. The air is never really sleeping, it's just waiting.
And that is a thought that will make me check the weather report a little differently tonight.
Thanks for diving in with us today.
Until next time.